Hello, everyone. This is the third part in a series of videos on the relationship between two quantitative variables. In the first part, we looked at the scatterplot to determine the form and direction of the relationship. In the second part, we used the correlation coefficient to describe the strength of an approximately linear relationship. And in this part, we look at the formula behind the correlation coefficient to gain additional insight of what the correlation really measures. Let me go to my textbook and show you what the formula of the correlation coefficient is. We see it given here in this yellow box, but before I go and explain what this means, let me remind you of z-scores. Remember that if we get a z-score, for instance, for the x variable, we just simply take the observed value, any observed x value, subtract the overall mean of all the x's, x bar, and then divide by the standard deviation of all the x's. So x is a particular value, x bar is the mean, the sample mean of all the x values, and s sub x is the standard deviation of the x values. For instance, if you get a z-score of -1, that would mean the observed value is 1 standard deviation below the overall mean of the x's, and a z-score of 1.5 would indicate that the observed value falls 1.5 standard deviations above the mean of the x's. We have z-scores for the x variable, and we have z-scores for the y variable. When you now turn to the correlation coefficient r, we see that to compute it, we take the product of the z-scores. We take the z-score of an x value and multiply it by the z-score of the corresponding y value. We then take the sum of these products. The sum is over all the possible pairs of observations you have. You can think of these are all the points in your scatter plot. Each point has a z-score for the x value, a z-score for the y value. You take that product, you sum up all those products, and then you divide by n-1. Let's go to the Scatterplots and Correlation app to visualize what this formula really means. I went to artofstat.com, clicked on Web Apps, and then clicked on the Scatterplots and Correlation app, which is this one right here. When you open that app, you will see the familiar data set where we plot internet penetration or internet use of 32 countries against their Facebook use. Let's focus on one particular country, Japan, which has an internet use of roughly 80% and a Facebook use of roughly 15%. Let's first find the z-scores, the z-score of Japan in terms of internet use and its z-scores in terms of Facebook use. I can get this automatically with the app by pressing on standardized variables. So if I select this option, I have Japan right here, and let's look at its z-score. Its z-score is positive for the internet use because its internet use, which remember was roughly 80%, is above, roughly 1 standard deviation above the mean of all the other countries. But its z-score on Facebook use is below, is negative, meaning its Facebook use is below the average Facebook use. If you go back to the original scatter plot, you see that the internet use of Japan is higher than the average, and its Facebook use, though, seems to be lower than the average, and that's indicated by their z-scores. Now, to obtain the correlation coefficient, we would take the product of the z-scores. We would multiply 0.89 zx times minus 1.27, the z times y. That will be one contribution. We'll do this for all the countries we have. You take the sum over all those 32 countries and then divide by n-1. And that will give us the correlation coefficient R of 0.61. Now, if you study the picture, you see that when you look at the standardized variables, we have 4 quadrants. All the countries, all the dots in the upper right quadrant in this one have both a positive z-score on the x-axis and a positive z-score on the y-axis. So their product of the z-scores is going to be positive. Take, for instance, Sweden, you multiply 1.56 by 1.14, cx times cy. That will be a positive number, and the same is true for all the other countries. The same happens for countries that are in this lower left quadrant. For them, both their x and y z-score are negative. look at Indonesia here, which has a negative z-score for internet use and also a negative z-score for Facebook use. If you multiply two negative numbers, you get another positive number. So all these countries in this quadrant and all these countries in this quadrant contribute, make a positive contribution to the sum of the product of the z-scores that we have seen. So switching back to the formula, for all those countries in here, c times x times c times y is positive. They make a positive contribution to the sum. On the other hand, all those countries, all those dots in the scatter plot that are in the upper left or lower right quadrant, their product of z-scores is negative. Let's go to Japan again, which has a positive x z-score, but a negative y z-score. Their product will be negative. And that's true for these three countries and for these four countries. Now, overall, you see that there's many more countries that are in the upper right or lower left quadrant. So overall, we expect the sum of the product of the z-scores to be positive because many more countries live here or here. Only very few countries, these 4 plus these 2 to be exact, so only those 6 countries of the 32 will make a negative contribution to that sum. And this lets us understand the correlation coefficient. The more points are in the upper right or lower left quadrant, the larger the correlation is going to be. Why? Because those dots, those points, those countries will make a positive contribution, whereas those dots will make a negative contribution, bringing the correlation slightly down. So let's look at a different example. Let's look at an example for a negative correlation. We've seen the gas mileage and weight data set before, where I plot the weight of a car against its gas mileage. Let's again standardize the variables. This will show that the Hummer, for instance, is far removed from the center. Its z-score is 2.4 on the weight. So its weight is 2.4 standard deviations above the average weight of all the cars. But what do we have now? We have most observations in the upper left and lower right quadrant. For all these observations, the product of the z-scores is negative. Here, here a negative x z-score multiplied times a positive y z-score, and for these countries, a positive x z-score multiplied by a negative y z-score. So there will be lots of negative contributions to that sum and only a few positive contributions, making the correlation overall negative. Finally, let's look at an example where there's not much of a correlation. We used the Tour de France data set in other videos before. This seems like a cloud of dots, not much going on here. So if I look at the standardized variables, I see there's about an equal amount of riders, in this case, of observations in each of the 4 quadrants. Yes, the correlation coefficient is slightly negative, so there seems to be a little bit more here, or they seem to have more weight, but overall, there's an equal amount of observations in each of the 4 quadrants, giving a value of the correlation that is close to 0 and revealing really no relationship. So I encourage you to play around with more standardizing the variables and playing around. And note, you can also upload your own data set if you want to, or type it in here to explore the correlation between 2 quantitative variables.